So, dear students, we'll continue. I think my audio is muted. Sorry. Is the PPT is visible now? Yes or no?
Yes, sir.
Okay. We have finished the heat treatment chapter. If there is any doubt, we'll discuss in the next class. Once again, I will explain briefly some of the important aspect of cooling curve as well as CCT diagram, that is the fundamentals requirement for your heat treatment chapter. Other than that, there is some derivations left beginning because December 3rd or December 1st week was the last working day. That's why I have done a little bit fast, especially this fracture and creep. There are two derivations, but as per your syllabus, it is not mentioned. But it was there in the earlier syllabus. Sometimes those who set the question paper, they will refer word question paper, they'll set the question. That's the one probability. And one more is the textbook is almost same. Some question paper, they will refer the textbook, they'll set the question. So that's why those two derivations, they're not mentioned specifically or explicitly in the syllabus. Still, there may be chance of asking the derivation, some related problems from module 2. That is one derivation from fracture and one more derivation from the stress relaxation. So now we are talking about the before. I think you have forgotten all those things. Just spend around 5 minutes. Fastly, I'll spend. The fracture, you are familiar. There are two types of fracture: tactile fracture and brittle fracture. And finally, at the end, you will get two fracture surface. Those things are very important. So after once you are apply the load, there is a small cavity will form. These cavity will join together. There are many small cavities or porosities will join together. It will form void, bigger void. So once load is applied further and further, so it will be fractured, or we can say that the new surface are generated. This is the one surface. This surface can be referred to the cone surface. There is a one more surface that is referred to the cup surface. That means some amount of energy was spent for generation of the two additional surfaces. So that is those surfaces are very important. Now we are talking about the derivation and theoretical aspect of fracture mechanism. So finally, after application of loading, two surfaces will be formed by absorbing sufficient amount of energy. So now here we have microscopic voids. So once load is applied, the voids will be formed. These voids will be joined together. These are the microscopic defect or voids. Those voids will be joined together, and finally it forms micro crack. If we apply the load, so further and further, so we will get two surfaces. To get how much amount of energy spent to generate additional surfaces, that is nothing but your fracture energy. There are two stages. One is crack initiation. This is the crack initiation. This last stage is the crack propagation. We can see one is crack initiation and one more is crack propagation. Here we can see this is the starting point. The void formation, it is nothing but a crack initiation. And here we can see the crack will propagate. Finally it forms crack fracture. These are the fractured surfaces. So finally we get two surfaces. So you're talking about surface now. What is the surface? So there are two surfaces are generated here. So the area of these two surfaces are referred as AS. Area AS. The amount of energy required to generate this single surface is referred as gamma S. Now I am giving some notations. So AS refers to surface area. This is the AS, the total new surface generated during the formation of the crack is given by AS. Now, how much amount of energy required to generate new surface? It is given by the surface energy. The surface energy is given by gamma S. Now, gamma S refers to surface energy or energy required to create the unit surface area or new surface area. You are talking about the brittle fracture. Finally you are talking about Griffith theory of fracture, which describes the brittle fracture, phenomena of brittle fracture. There are many theories are there. So one of the well established and accepted theory is the Griffith theory of brittle fracture. So again, you can see there are two surfaces. So finally, these two surfaces will be joined together and forms. So now I am telling only what is the fundamental required for our derivations. These things already you have studied. This is the fracture point. The point B is the, if it is a brittle material, the point B is the fracture point. If it is highly ductile material, the fracture B dash is the fracture. So before it undergoes the fracture, if you consider brittle material, the AC refers to the total strain it undergone before the fracture, or total amount of strain is required to fracture the given specimen. If it is ductile material, it undergoes huge amount of strain. It includes plastic deformation as well as elastic deformation. So now you can see this is the fracture point. Again, this is the fracture point. So this is the ductile failure. We'll get almost point cone shape. It is very sharp cone here. If it is brittle, we'll get almost flat surfaces. If it is moderate ductile material like a steel, aluminum, copper, we'll get cup and cone fracture. So we can see these are the actual fractured surfaces. We can see here. This initially it is a single material, single component. It is fractured into two surfaces. This is one surface and this is one more surface. And how much amount of energy absorbed by the material to generate these two surfaces is nothing but a fracture energy. It is also referred to as gamma S. Gamma S, some amount of this calculation you are done in your material testing laboratory, even for impact, Charpy impact test as well as ISOD impact test. So finally you got how much amount of energy absorbed by the material before it fractures. Now you are concentrating on how much amount of energy is required to generate new surfaces. Now we'll come to our derivations. I hope you are understand. You studied the physics. Along with that, you know what is the between the two atoms. If the atomic distance is very small, there is an attraction forces. If the atomic distance is too large, you're talking about in terms of too large means not in meters or centimeter. You're talking about in terms of angstrom or nanometer or in micro, not in the micrometer also. You're talking in terms of nanometer. If the atomic distance is more and more, there will be repulsive forces. If the atomic distance is very small, two atoms are very close, there are attractive forces. I hope if you know those fundamentals, the physics fundamental, then this derivation will be easy. So now, we required some equation. So finally, we require, fine. So what is fracture? So fracture is, so in the macroscopic level, imagine you have the original workpiece impact testing specimen. It is a single piece. It is fractured into two surfaces. But what is happening within the material? That is important. So anyone can tell what is fracture? Fracture is nothing but a process in which the material is fractured into many components. You can give the example of fracture of the glasses, fracture of the stones, etc. That's a general understanding. Being a mechanical engineer, you have to give some more in-depth theoretical fundamentals about how exactly fracture takes place in the material. So once glass fractured, the overall surface area will be increased. If fracture, imagine you have a chalk piece, if you pull the chalk piece, it's broken into two pieces, it will generate two more new surfaces. The overall surface area will be increases. To increase the overall surface area, fractured surface area, we already pulled the fracture chalk piece or bent the chalk piece, already you have spent some amount of energy. That is everything you are talking in terms of macroscopic level. In the microscopic level or atomic level, so there is a breaking of bonds between the two atoms. Wherever there is a fracture region, crack propagates or whatever it may be, there's the strong atomic bond. So whatever the amount of stress you are applied, if you talk in terms of mechanics of material, so whatever the amount of force you are using or whatever the amount of energy you are spent for fracture, so that should be able to break the atomic bonding. So thousands of lakhs of atoms are there. If you consider 10 by 10 centimeter area, there may be lakhs of atoms. So those atomic bonding, each atom having bonding with another atom, those bonding should be broken to get fractured surfaces. That is in the overall, if you consider the overall material, that is the case. In the macroscopic level, the fracture refer to generation of two new surfaces, a separation of the single component to two or more by the application of forces. The microscopic level or in the atomic level, the lakhs of atomic bonds are broken. Finally, it is fractured into two or more surfaces. Now, instead of considering the macroscopic level of thousands of atoms, so for our consideration, for derivation purpose, we have to make it very simple. You are considering only two atoms. So you are considering only two atoms. We can see here. This is the one atom, then this is the one more atom. The initial atomic distance. Can you see the diagram? Can you see the diagram? PPT. Yes or no?
Yes, sir.
Okay. So now you are concentrating only on one atom, two atoms, the two adjacent atoms. So initially there is an equilibrium distance. So these are the two atoms initially at equilibrium distance of A naught. When it is pulled through some external forces, then atomic distance is increased to A. So now A naught is the initial equilibrium distance. So once the load is applied, imagine you are applying tensile loading, the atomic distance is increased, bonds are not broken, still there is an atomic bonding between two adjacent atoms there, but the distance between the atoms is increased from A naught to A, we can see. So now equilibrium distance is given, this is a cohesive force. The cohesive force is nothing but attractive forces, the bonding forces. So when it at the equilibrium position A naught, the cohesive force is almost zero. Now we have applied the force. If you try to pull, so imagine you are pulling in the outward direction, the atoms will try to move in the inward direction. The best example I can give is, imagine you have a spring, the helical spring, you try to compress in the downward direction, the spring is trying to push you in the upward direction. In the similar way, you are trying to pull the two atoms apart, but these two atoms are trying to move together because of the cohesive forces. So now at equilibrium distance, the cohesive force is very, very less. It is almost nil. So when you try to pull the atoms, the cohesive force will be increases. You can see here, the cohesive force, it is not just your stress, the cohesive force is increases from almost 0 to the maximum value, that is represented as sigma max. It is nothing to do with your ultimate tensile strength or fracture strength, etc. We are talking about only two atoms. at equilibrium distance, cohesive force is 0. If you try to pull the two atoms together, cohesive force increases. It reaches maximum distance. Then if the distance is, after reaching some threshold value of the distance, or after reaching some critical value, imagine distance is that to be 1 micron, not 1 micron, around 100, around 1000 angstrom. So then cohesive force, attractive force is bit decreased. It's almost like a magnet. If the magnets are kept very close to each other, then there is a more attractive force. If you try to pull apart, then attractive force will be decreases. Then after certain distance, so it will lose the attractive forces. In the similar way, initially we have maximum cohesive force. After reaching one distance, this is the atomic distance. The distance between the two atoms reaches A, then the cohesive force becomes 0. Then there is a repulsive force, that is referred by negative sign here, dotted line. So you are not concentrating on the repulsive force, you are concentrating more on cohesive force. So once you are able to apply sufficient amount of the stresses or load to overcome this cohesive force, then we can break the atomic bonding. We can imagine, we can say, you have to apply certain amount of load. So initially huge amount of resistance to the separation of the bonding. Then after some times, after reaching certain atomic distances, so then what will happen is their coercive forces will decreases. It comes to 0. That is nothing but a almost fracture point. That means you have to apply so huge amount of force to move the atoms up at a distance from A naught to A. That is nothing but a maximum cohesive force, or sigma max. So same sigma max can be written in the equation form. So now at any point sigma is equal to sigma max into sine, because it follows, you are assuming that it follows the sine wave. So we can find out what is the cohesive force at any distance A. We are considering only two distances. So one distance is A naught and one more extreme distance is A. We are considering only two distances. In both the distances, cohesive force is 0. In between, we have maximum cohesive force sigma max. As it follows the sinusoidal curve, so now we can write the equation, sinusoidal equation, to find out what is the cohesive force at A1, what is the cohesive force at A2, what is the cohesive force at A3, what is the cohesive force at A4, etc. That you can write in the form of sinusoidal equation. So now at any distance, any atomic distance between the two adjacent atoms, the cohesive force is given by sigma max into sine 2 pi x by lambda. Lambda is nothing but wavelength of the sine curve. We can see here. The lambda is nothing but wavelength of the sine curve. So 2 pi x is the change in distance between the two atoms. The change in distance between the two atoms, what is the formula? What is the change in distance between the two atoms?
A minus A naught.
That is nothing but A. No, you can see this diagram.
A minus A naught.
That is nothing but A. No, you can see this diagram.
Yes, sir.
It is. I think there is a rebounding of sound. Okay. It is a change in distance. A minus A naught is nothing but x. X is the change in distance between the two atoms. So now already we have sine curve. It is nothing but you are writing in physics, x is equal to capital letter, small or lowercase letter x is equal to capital letter x into sine omega t divided by lambda or 1, 2, 3, etc. Thus in the similar way, by using your your mathematics equation, we can write. So what is the cohesive force at any distance between the two atoms? So now equation for x is also given. X is equal to A minus A naught. And sigma max is given by theoretical cohesive strength. So theoretical cohesive strength is, so what is meant by theoretical cohesive strength or practical cohesive strength? Suppose if you see the steel, the Young's model of the steel is 200 GPa. imagine there is no defect in the material. Defect in the sense, not surface defect or some your manufacturing defect, or you're not talking about the forging defect or casting defect or any other manufacturing defect. If there is no defect in point defect, line defect, or volume defect, or surface defect, those defects we studied in your first module. If there is no defect in the microscopic level or atomic level, some atoms may be missed from the unit cell. So some new atoms may be entered. Those are the defects we studied: point defect, line defect, surface defect. Like that, many types of defect we studied. And if there is no defect in the material, then so that is nothing but your cohesive, theoretical cohesive strength. So strength of the material without any defect, it not necessarily only the macroscopic level or fabrication defect, even microscopic level or atomic level, there is no defect. Then that type of strength is referred as the theoretical cohesive strength. In the theoretical, if you do theoretically, the Young's modulus of the steel is 200 GPa into at least 100 to multiplication by 100. 2000 is almost 20,000 GPa. 20,000 to 2 lakh GPa. If you consider the original theoretical formula, atomic formula, etc., so then the Young's modulus of steel is around 20,000 GPa. Because there are some defect in the material, the actual value of the Young's modulus, when you conducted the experiment, we got around 200 GPa. But actual value is 200 GPa, but theoretical value may be theoretical strength of the material, Young's modulus of the material, let it be around 20,000 GPa. That is the difference between theoretical value and actual or practical value. Practical value is 200 GPa. Theoretical value, if there is no defect in the material, it may be around 100 to 1000 times the actual value. That is nothing but 100 to 1000 times the 200 GPa. We can imagine around it comes around 20,000 GPa to 2 lakhs GPa. That is the theoretical Young's modulus of the material, but in practical it is only 200 GPa because of the defect in the material. Those defects we studied in first module. Now sigma max is the cohesive, theoretical cohesive strength. So now sin x is, we know from the trigonometry, for this very small value, because atomic distance is in terms of the angstrom. The x is very small value. For very small value, in mathematics you studied the sine of theta is equal to theta, sine of x is equal to x. So now after substitution, you will get this equation. From the Hooke's law, we know that Young's E is equal to sigma divided by epsilon. Sigma is equal to E into epsilon. Those formula you know. So now finally we have the equation for the sigma. Sigma is equal to E into epsilon. That you studied in your mechanics of material. Then, so we have to get the formula for the strain also. Strain is change in length divided by original length. The change in length is nothing but, so once you applied load, there is an atomic distance is increased. So what is the increased atomic distances when you applied the load? That is nothing but a change in length. That is already we have discussed. A minus A naught divided by A naught is nothing but your strain value. So we are finding out strain in the atomic level, not in the macroscopic level. You have to understand what you are doing in your mechanics of material. You are studying the strain in the macroscopic level. Now you are finding out the strain between the two atoms in the atomic level. So initial distance is between the two atoms is A naught. So after application of the loading, so distance between the two atoms are increased to A. The net change in deformation is given by A minus A naught divided by A naught. That is nothing but x divided by A naught. Now we can write E is equal to, we know that by using this equation. So by using E epsilon is equal to x divided by A naught, and E is equal to sigma divided by E. So finally we get equation for sigma. Sigma is equal to E by epsilon. The epsilon is equal to A naught by x, that goes to up. That's only simple calculation. So now we have the equation 2 and equation 3. Once you combine those two equations, so we'll get equation for sigma max. This is the equation for the sigma maximum. This is the maximum amount of stress required to get to break the cohesive strength of the material or to break the atomic bonding. So now, when fractures occur in the brittle solid, all the energy spent in producing the fracture goes into creation of two new surfaces. That's why I given the example of surfaces. So why I'm telling you surfaces, you are applied amount of load. Even imagine simple, forget about your high complex engineering. You take one biscuit, you pull it, it breaks. It will form new surfaces. If you consider it will form new surfaces, two new surfaces. So already you have spent some amount of energy. If you keep one biscuit on table, it will not break into two or more pieces. No magic. You are applied some amount of load. It may be in the any form. So finally, so once it crosses the sigma max or threshold value of the load, then only it fractured and finally it forms two or more surfaces. It will create more and more surfaces. So the same thing is shown here. When fracture occur in a brittle solid, you are talking of the brittle material. The ductile material is a more complex phenomena is involved. There may be twinning, there may be slipping, there may be other hardening process. Then it will be more complex for the ductile material. The brittle material fracture mechanics is very simple. So all the energy spent in producing the fracture goes into creation of two new surfaces. That means you have spent some amount of energy, even the tensile test also in the macroscopic level, you have applied certain amount of energy or load, and because of the loading, the specimen is fractured into two pieces. And it finally forms the one surface on the cup part of the specimen, the one more new surface on cone part of the specimen. So fracture mechanics is not just your small topic in your module. The fracture mechanics is a type subject, separate subject itself. Even we have the PG machine design. There is a separate subject. It's a core subject. Even engineering also, we have I think 7th semester, 8th semester. You have one more elective subject, the fracture mechanics, especially for the critical component, the spacecraft component, aircraft component. Suppose you are talking about high-speed bullet train. So those fractures are very important. Most of the components are failed by fracture or sometimes by fatigue, sometimes by the creep when it is subject to higher and higher temperature. So now you are talking about the work done per unit area of the fracture in creating the surface in the area under the stress strain displacement curve. Now you are finding out some amount of work is done. Imagine you are opening the paper. Imagine you have to close the book. Just you try to open some particular page, that will be page number 100. So when you are opening that particular page, it will generate two new surfaces. You have spent some amount of energy, some amount of work is done to open the book. So once it is open, initially there are outer two surfaces. I am talking about the surface exposed to the outside. So once you open it and hold it, the bottom we have two surfaces, top also we have the two surfaces. Imagine you are open exactly at the mid stage of the test book. So that means you have spent some amount of energy, you have done some amount of work. For that work, so you are going to write equation. Finally, you have to write in terms of equation. So now work done. The work done per unit area of fracture in creating the surface. You are creating new surface. So in the area under the stress displacement curve, the stress displacement curve already was seen. This is the stress displacement curve. So the area under this curve we want to find out. Area under this curve is given by. So your value is ranging from sigma naught to a naught to lambda by 2, the right side. Lambda by 2 a naught. That is the two limits, a naught to lambda by 2 a naught. So that I'll show you what is. This is a naught. From this point to this point, the total length of the sinusoidal curve is lambda. But what is the amount of energy spent to overcome this cohesive forces? Only this part, upper part of the curve. That means from a naught to this point is total length is lambda. this point is lambda by 2. The lambda by 2 plus A naught. That means you are moving from A naught to A naught plus lambda by 2. This is A. We can say A. So total distance A is equal to, we can write it as A naught plus lambda by 2. This distance is A naught. This distance is lambda by 2. Now we can write A is equal to A naught plus lambda by 2. Finally, you are going to find out area below this curve. If you are able to get this area below this curve, we'll come to know that how much amount of energy is required to break the atomic bonding or get new fractal surfaces, or when the component fails. Finally, being an engineer, you have to understand. So when component fails, once you apply 100 kilonewton load or 1000 kilonewton of load or 500 kilonewton load, at what point the component fracture, that value we want, that value is given by area below this curve. That is nothing but your stress versus the displacement curve. It may be a simple equation, but it has its own meaning. So from you are starting from A naught to A. So A is given by A naught plus lambda by 2. But lambda is already, we have the equation. Lambda is equal to sigma max. This already you have seen the equation. Then after integration, etc. That's all. So you will get the U naught is nothing but lambda into sigma max divided by pi. The U naught is the energy is required to break the atomic bonding or to form new surface. That you have to remember. The amount of energy required to break the atomic bonding and to form new surfaces. Suppose you have a stone, you have to break it into two pieces, you have to break the hammer, you have to break it. How much amount of energy is required to break the stone? Without breaking the stone, you should have some theoretical, for each and everything you cannot test the test. We require some theoretical modeling. So for that, so amount of energy required to form new surface is given by lambda into sigma max divided by pi. So U naught is equal to the energy required to create the two new fractured surfaces. So that is given by. So now I have already told it can generate two surfaces. The amount of energy, I think if you go to this, so now you can see the two surfaces are generated. Left side surface is one, and right side surface is one more surface. So the amount of energy spent to create left side surface is, let it be gamma s. Gamma s. The amount of energy spent to create the right side surface by fracture, it is gamma s. And total surface area is, the total amount of energy required is the gamma s plus gamma s. Finally, we get 2 gamma s. To generate one surface, we required gamma s. To generate two surfaces, how much amount of energy is required? To create one surface, the amount of energy required is gamma s. To create two surfaces, what is the amount of energy required? Simple calculation. To purchase one banana, that will be 1 rupees. To purchase two banana, how much amount is required? 2 rupees. In the similar way, to generate one surface, the amount of energy required is gamma s. To generate two surfaces, the amount of energy required is 2 gamma s. Same thing is shown here. So not only mathematically, don't derive this equation like a mathematical derivations. First, you have to understand. So that's why. So this is the, on the left side, this is the total amount of energy required to break the surfaces. So that's also equal to amount of energy required to form the two surfaces. Gamma s refers to the amount of energy required to create one surface, but during the fracture, we are assuming that a standard fracture, it will generate two surfaces. So the amount of energy required to create each surface is gamma s. Because it creates two surfaces, we have 2 gamma s. The finally we get lambda. This is the formula for the lambda. Now, what is the maximum amount of energy spent to fracture or to break the bonding is given by this formula. The auto simplification we get. using this equation 6 and 4. Those things you can do it yourself. So 2 is constant. The pi is also constant. E is the Young's modulus of the material. That's also constant. Gamma S is the property of the material. E is the property of the material. Gamma S is also property of the material. Into 2 pi A naught. This sigma max not coming here. So this is sigma max. So finally we get sigma max square. So now if you see this equation, E is constant, gamma S is constant. The atomic distance is also constant. For the steel, the atomic distance we know what is the diameter, atomic diameter in terms of angstrom. It may be 1 or 2 angstrom. So that is everything is known. So once you know that, we'll come to know what is the amount of energy required to break the bonding between the two atoms. That is the property of the material. If you consider steel, so the amount of energy required for breaking the bond to fracture the surface is more because Young's modulus of steel is more. If you consider same aluminum, the Young's modulus of aluminum is less. So hence, the small amount of energy is required to break the bonding between the two atoms to get the fractured surfaces. Once you understand, then the Griffith theory of fracture for the brittle material is very, very simple. So finally, we required some amount of energy to break the atomic bonding to form new surfaces. So now we are talking about the Griffith theory. So why we formulated Griffith theory is that already I have discussed. The theoretical cohesive strength of an ideal crystal having no imperfection in it is around 100 to 1000 times the strength of the real material normally observed. I give an example. The Young's modulus of the steel, it's a polycrystalline material, is 200 gigapascal. That is the practical value. The theoretical value of Young's modulus of the steel, if there is no defect, it will be around 20,000 GPa. There is a huge difference between theoretical value as well as theoretical strength of the material as well as the practical strength of the material. So Griffith is trying to give the explanation why there is a huge difference between theoretical strength and actual strength of the material. So now we can say that the Griffith originated theory to explain the discrepancy between the theoretical and observed values. To understand better, the theoretical value is a little bit 200 to 20,000 GPa for steel. The actual value of E may be around, observed value is only around 200 GPa of the fracture strength of the material. He assumed that real material under consideration is not defect free. We know that there may all materials having defect, but there may be no defect in the sun. There is no surface defect, there is no fabrication defect, but there may be always some inbuilt defect in the material. The materials in the inbuilt material in the sense, the defect in the crystallographic level, not in the macroscopic level, crystallographic level. It may be missing of atoms or missing of line of atoms or missing of group of atoms, etc. Those are the defect in the material, not necessarily your defect during your casting process, what you say, porosity or etc. You have studied different types of defect in the material. So now Griffith tried to explain so why there is a huge difference. The one of the reason is so defect in the atomic level, defect in the grain level, defect in unit cell level. So those are different level of defect. So again, you are talking about, so whenever there is a new cracks is formed, microscopic cracks are joined together, the crack is formed when propagates and result in a brittle fracture. Initially, we have small crack, microscopic crack. Those cracks will propagate and finally it forms the macroscopic fracture. What you studied in your empty lab, we studied how the microscopic cracks are generated. You are not seen. So finally, the macroscopic crack propagation you have seen, and finally the failure because of the fracture you studied. But a lot of things are happening in the microscopic level that you have to remember. But you are talking about the elastic energy. What is elastic energy? What is elastic energy? So suppose you are compress the spring, some amount of energy is stored in the spring. That is because of the deformation. So because of the deformation, this energy is also referred as the strain energy. That is nothing but your strain energy. When your spring is compressed, the spring is undergone strain, and if you leave the, you are try to push the spring in the downward direction, and if you leave your hand in between, it come back. So what is the amount of energy is required to come back to the original position? So that is because the energy is stored in the spring in the form of strain energy. That we can see in the macroscopic level. I am giving the example of spring, helical spring. You are pushing the spring in the downward direction. The spring is compressed. The spring is deformed. Because of the deformation, there is strain. And whatever the amount of spent energy is spent to compress the spring, that amount of energy is stored in the spring in the form of strain energy. So we can say that strain energy is stored in the metal during loading. Even in the, when you apply tensile load, so there is a huge amount of energy you are applied. You are noting down what is the amount of load you are applied, etc. So during that particular loading also, there is a lot of energy stored in the material. Those energy is stored in the form of strain energy. This can be stated as a crack will propagate and result in fracture when the decrease in elastic strain energy at least equal to energy equal to create the new surfaces. So you have to understand, because one aspect you have to remember is what is the strain energy. The strain energy may be plastic strain energy or elastic strain energy. Now you are talking about only elastic strain energy. That's the first part. That's the one energy is involved. The one more energy is you are talking about the surface energy. That is nothing but a gamma energy, gamma S. So now when crack will propagate, there are two energies is there. So one is strain energy. It is nothing but elastic strain energy. So one more is surface energy. When elastic strain energy is at least equal to the energy, at least equal to energy equal to create the new surfaces. So we have elastic energy, elastic strain energy. That particular elastic strain energy should be able to create new surfaces. Then only the crack will propagate, generates and propagate, and finally fracture will take place. That's why the same thing is given. A crack will propagate and result in fracture when decrease in elastic strain energy at least equal to energy required to create new surfaces. Required, it is not equal. Energy required to create new surfaces. One is already I given, to create new surfaces, we require some energy. That energy we obtain from the elastic strain energy. Elastic strain energy we are getting in the material by metal deformation. So we are getting the deformation in the material because of the loading. So in your UTL, the loading is your hydraulic loading. In simple way, you can remember. So we can explain Griffith theory in different form. A crack will propagate and produce brittle fracture when there is no net energy change in the system with any increase in the crack length. So I am talking about the simple pendulum. The pendulum bob is in the horizontal position. It has maximum potential energy. When it is in the vertical position, it has maximum kinetic energy. During the movement of pendulum from horizontal position to vertical position, so net change in energy is zero. The change in energy is zero, but the energy changes from kinetic energy to the potential energy, or potential energy to kinetic energy. The energy available in the pendulum bob remains same, but only thing is it changes its form from kinetic energy to potential energy, or potential energy to kinetic energy. Suppose when it is horizontal position, the energy in the pendulum bob is, let it be 100 joule. 100 let it be 100 joule. When it is in the vertical position also, it is 100 joule. But when it is in the horizontal position, it is the potential energy. When it is when it comes to vertical position, after rotating through 90 degree, you can imagine pendulum bob you studied in your physics. Again, it has energy, but energy is in the form of kinetic energy. Again, total amount of energy is same 100 joule only. So now, straight away we'll go for the derivation. We have less time. So now this is the plate having small crack. The length of the crack is given by 2c. 2c is the length of the crack. It is also equal to diameter of the crack. If the elliptical, if we can assume the crack is having almost circular cross section, it is elliptical cross section, but still we assume that it is circular cross section, and length of the crack is given by 2c. So now the area of the crack is, this side is 2c, other side is 2c, then finally we get 4c, the other side is 4c, or we know that if it is what is the area of the circle? Pi r squared by, what is the area of the circle? Pi d squared divided by, pi d squared divided by 4. So pi into d square is 2c square by 4. 2c square is 4c square by 4. The finally end with the area of the crack. We are talking about the surface area of the crack. The surface area of the crack is pi c square. The pi c square is given by, the area of the circle is given by pi r square. So r is pi d square divided by 4. The d is 2c. And after substituting this, so we will get pi r square is nothing but area of the crack. So multiply by depth of the crack is, if it is 1 meter, then this refers to total volume of the crack is given by pi c square. So one is elastic strain energy per unit volume released in order to form the crack is sigma square divided by E. Some amount of energy is required to propagate the crack or to create the crack. That energy is referred as elastic strain energy. That elastic strain energy is given by sigma square divided by E. This is the elastic strain energy that is given by sigma square divided by E. That we can get, it is nothing but area below the stress strain curve within the elastic limit. For spreading of the crack, so we require, the energy required per unit volume is sigma square divided by E, and total volume of the crack is pi c square. Pi c square refer to total volume of the crack. Total volume of the crack, because depth of the crack is only one unit, and diameter of the crack is 2c, and pi r square by pi d square divided by 4 become pi c square. So pi c square refer to volume of the crack. The sigma square divided by epsilon E is nothing but the amount of energy required to get the crack per unit volume of the crack. Now you are multiplying by the total volume. So now we'll come to know what is the total energy required to create the crack. That is nothing but sigma square divided by E into pi c square. That is from the mechanics of material principle. From the mechanics of material, we'll come to know the amount of energy required to generate new crack. This is the amount of energy required to generate new crack. But we have one more energy, that is nothing but surface energy. We know that surface energy of the material. Surface energy of the material is material properties. Surface energy is given by gamma S. Gamma S refers to surface energy. But there are two surfaces. So now, what is the total surface area? This side is 2c, other side is 2c. The total surface area is 4c into 1. The surface area is nothing but the length of the crack into length of the crack into depth of the crack. Length of the crack is 2c plus other side 2c, 4c into 4c is the surface area of the crack. This 4c is the surface area of the crack into gamma s. Gamma s refers to the surface energy, or how much amount of energy is required to get unit area of the crack. The energy required per unit area is given by gamma S, but our total surface area is given by 4C. This is the amount of energy required to generate the crack. So now these two energies should be equal, because this is the energy obtained from mechanics of material concept. This is the energy obtained from surface area concept or surface energy concept, and these two energies should be equal. So once you equal to these two, the total surface energy gained by the creation of two crack surfaces is given by 4C gamma S, that is 1, and net energy is elastic energy plus surface energy. We have the formula for elastic energy. This is the surface energy. But so total energy of the system remains constant. We have the basic principle, total amount of energy remains constant. We have put some amount of load, your applied load. Because of load, there is a deformation. Because of the deformation, there is a strain. Because of the strain, there is a material is undergone deformation. That whatever the amount of energy spent is stored in the material in the form of deformation energy. So one is deformation energy is nothing but UE. The one more is surface energy. Net change in the energy remains is equal to 0. There is a change in energy, but net change in the energy is equal to 0. Don't think that energy of the system is not equal to 0. The net change in the energy of the system is equal to 0. Net change in nothing but differentiation of change in energy of the system is nothing but differentiation of the energy term with respect to d by dx of the energy equal to 0. The dx is nothing but your crack length, dc, and finally we get sigma f. So sigma f is nothing but the fracture energy. We'll get, after simplification, etc., we'll get sigma x is nothing but fracture strength of the material in the presence of crack is known as fracture strength. So whenever you're talking about the fracture, you are assume that already crack is present in the material. But there is a difference between fatigue and fracture. During the fatigue loading, the crack is nucleated. You should be able to understand between the fatigue failure and failure because of the fracture. During the process of fatigue loading, the crack is nucleated, it will be propagated and finally fade. But in the case of fracture, the crack is already present in the material. Like what you've done is the impact testing material. You have U notch, that is nothing but a macroscopic crack. Or there may be microscopic crack in the material because of a defect in the material during production process itself. Either it may be casting or it may be forging, etc. So now we are saying that so sigma f is the fracture strength of the material in the presence of the crack is in the presence of crack of known length. So our known length of the crack is 2c. Once you know the crack length for a given crack length, so what is the strength of the material? Suppose we have the beam in the macroscopic level. The beam is having 1 mm crack, 1 mm thickness crack. Then we can find out what is the strength of the beam. If the crack length is 2 mm, what is the strength of the material? If the crack length is 4 mm, there is no strength, building may collapse. It cannot take more amount of load. So that's why the Griffith theory says that once you know the crack length, so we can find out so whether system fails or not. Even our bones also there may be small crack. Even buildings also there may be small amount of crack, but building will not collapse. This is a practical experience I think we had. Beams also there may be crack, small amount of crack. We can see even buildings also we can see there is a crack. Because only when it exceeds certain value, then only crack will propagate and failure occurs. Or when crack will propagate and failure occurs, so only when it is subject to huge amount of loading, then only the crack will propagate and failure takes place. Otherwise, it will not fail. Most of the times, the buildings will not fail. Only during earthquake or tsunami, buildings may fail because there may be crack in the building itself. Because of the earthquake, additional load is acting on the buildings. So already crack is there in the building. Because of additional loading, the crack will propagate. The finally fracture, building may collapse, or some structure may collapse during tsunami or during huge wind, etc., especially tall building, etc., already crack is present. Because of the loading, crack will propagate and finally the failure takes place. So this is the derivation. Sometimes the Griffith theory of fracture is there. There may be small problems by using this formula. We have done some problems. We are not derived in detail. Just I explained what is Griffith theory in the beginning. I thought of explaining. It may come for your examination also. For your third test, the portion is the others material. I think it is a module 4 or 5, other material, not composite material. So one more is heat treatment. The module 3 and module 5 are for your test portion. There is no module 2 because your iron carbon diagram, phase diagram, everything will comes under module 2. I will not include module 2. Only module 3, that is complete heat treatment chapter, is there for your test. Then one more is other material like ceramic material, plastic materials, piezoelectric materials, many other type topics you have studied. That will be there for your test. 2 module 3 as well as module 5. If you have any doubt, you can I can give you the clarification. There are small problems are solved in the Punish textbook or any books refer on related to the fracture. There is only formula already we are derived. By using this formula, you have to substitute the value. That already we have done 1 or 2 problems. Once again, go through this the derivation. You practice this derivation. Try to understand the basic concept involved in the fracture mechanics. One is surface energy. That is how much amount of energy is required to generate new surface. Generate new surface is nothing but the propagation of the crack. So one more energy is your strain energy, or how much whatever the amount of load you are applying during tensile test. That finally it will be stored in the material. That energy you can consider as a strain energy. Your applied load, because of loading, there may be deformation in the tensile testing. There may be elastic deformation as well as plastic deformation. The initial level, there is only elastic deformation. So because of the elastic deformation, there is an elastic strain. So whatever the amount of energy is spent or applying the load, that will be stored in the form of deformation energy or strain energy. But net deformation energy plus net strain energy plus net surface energy equal to constant, or change in energy is equal to 0. By knowing that, by differentiating the strain energy plus surface energy, we will get the Griffith equation, or the strength of the material with the presence of crack. There is a small derivation there on stress relaxation that I'll do in the next class. We have completed almost all portions. There are small portion topics are left out here and there. We are not covered in detail, but you have sufficient time to cover. Don't worry. Those are, I think, you entered your US number. Okay. Those are not entered your US number. You enter. Don't enter twice. Just you can scroll down this chat box. If you already entered, if you have a doubt, you can check this whether your name is entered or not. If it is not entered, then only enter.